Welcome students to today's lecture, in which I am going to put a full stop to the topic inverse reactions. Last lecture was fully on inverse reaction only, and as I have mentioned two more topics in the previous lecture initial contents, energy production and mean lifetime. Those topics will be covered in today's lecture. What are the important takeaways from the discussion on inverse reactions? Number 1, negative Q value reactions plays important role at high temperatures, because at the high temperatures particles will gain enough energy to induce reaction in reverse order. So, when reaction proceeds through reverse order, whether there will be any change in the cross section value? Yes, there will be change in the cross section value, but the laws governing the nuclear reactions do not change with the direction of the reaction. So, the principle of time reversal invariance has been discussed in detail in the previous lecture, and you need to come up with a general representation of the cross section of a nuclear reaction, and it was the product of 4 terms. Number 1, pi lambda square, where lambda is the reduced de Broglie wavelength. Number 2, statistical factor represented by omega. Number 3, term taking into account the Kronecker symbol. Number 4, the matrix elements product, because that is the term which considers the interaction mechanisms of the nuclear reaction. Entrance channel to the Coulomb compound nucleus excited state can happen through one type of interaction. I mean, it could be through weak, strong or electromagnetic. And compound state to exit channel, which is giving rise to nuclei of types 3 and 4. It can happen through different mechanism. They need not be the same, but we have seen the ratio of the cross sections does not have any presence of the compound nucleus. So, that shows clearly that by measuring cross section in one direction, one can measure the cross section in reverse direction by taking the values of reduced mass and spins of the particles and all those values. Then I have written the ratio of the reaction rates in terms of Q value and temperature. Okay. So, in today's lecture I am going to discuss little bit about inverse reactions, some main features are left, and then I will discuss mean lifetime of a nuclear reaction and the energy production in stars in terms of reaction rate. Very brief explanation I will try to give. Okay. So, let us go forward. So, I have discussed recap, that is inverse reactions in the previous lecture whatever covered, and in today's lecture I will complete the inverse reactions by taking into account an example for photo-disintegration. Why? Because in the previous class I have taken 1 plus 2, 3 plus 4 and 3 plus 4 giving rise to 1 plus 2. Nowhere gamma is involved, right? And if gamma is involved, how the cross section ratio and reaction rates ratio will look like, that I will discuss in today's lecture. Okay. And then the energy production in stars and the lifetime of the nuclear reaction I will discuss. All right. So, the reaction rate ratio, when you consider forward and reverse reaction, is given as sigma V 3, 4 and sigma V 1, 2. What does it mean? Rate of inverse nuclear reaction divided by rate of forward nuclear reaction is proportional to e to the power of minus q by kT I have written in the previous lecture, if you remember, right? Because the terms preceding this exponential term, their order is of the unity. Now, numerically, if I want to express this, and you should know how to convert this, it is proportional to e to the power of minus 11.6 Q6 divided by T9, where Q6 is in MeV and T9 in gigakelvins, right? T9 is 10 to the power of 9, 1 T9 is 10 to the power of 9, 2 T9 is 2 into 10 to the power of 9. So, numerically having this kind of values helps us to come up with some numbers regarding the ratios, and you please do calculation by taking different values of Q and by taking different values of T, of course, in terms of 10 to the power of 9 gigakelvin, and you will observe that the reaction rate ratio is very sensitive to Q value. You can please check yourself, and at high temperatures the inverse reaction, that is ratio, becomes significant, very significant. If I start from 0.1 gigakelvin to 10 gigakelvin, the ratio ranges from 10 to the power of minus 50 to 10 to the power of minus 2. So, this signifies the role of inverse reaction at high temperatures, Now, we have seen the rate of the reactions in forward and reverse direction, right? What about the total reaction rate? I repeat, what is the total reaction rate in the star at a particular temperature? So, the total reaction rate can be expressed as the difference between forward and inverse reaction, right? Total reaction rate R is equal to R12 minus R34. So, if I expand this, this gives me the number density N1 N2 divided by Kronecker symbol delta 1 2. This is the general expression for the reaction rate, right? Total reaction rate is number density divided by Kronecker symbol term and reaction rate minus N3 number density of nuclei of type 3 and nuclei of type 4 1 plus delta 34 sigma V 34. Now, using the expression for reaction rate ratio, I can write down this total reaction rate as sigma V 1 2 divided by 1 plus delta 1 2 N1 N2 minus N3 N4 2J1 plus 1 2J2 plus 1 divided by 2J3 plus 1 2J4 plus 1 mu 1 2 reduced mass mu 34 to the power of 3 by 2 e to the power of minus qt. All right. So, again in this expression you can see that the total reaction rate is depending on the e to the power of minus q by kt and of course, reaction rate of 1 and 2 entrance channel. So, this is how one can express total reaction rate in a star by considering the both forward and inverse reactions, So, with this, let me stop the discussion of inverse reactions considering particles as not photons. What if one of the species is photons? Okay? One of the species is photons. How it looks like? I have already discussed what is photo-disintegration and what is radiative capture reaction. Okay? Photo-disintegration, okay, is nothing but is the reverse of radiative capture, right? Radiative capture. Let me give one example. For example, if you take the proton reacting with carbon 12, okay, it gives rise to 13 nitrogen plus gamma, whose Q value is plus 1.95 MeV. Now, if I go for the reaction reverse order, if gamma is available with sufficient energy, it can react with nitrogen 13 produced in previous reactions, giving rise to proton plus 12C, and for this the Q value is minus 1.95 MeV. So, here a heavier nucleus, that means N13, is disintegrating into splitting into lighter nuclei. Okay? This is called as photo disintegration, and capture of proton by carbon 12 is giving rise to gamma emission. So, that is called as radiative capture reaction. Okay? Now, as I have discussed in the previous lecture, at high temperatures the photons have enough energy, okay, of the order of MeV, and they can induce photo-disintegration reactions, and the rate of nuclear reactions can be given as induced by gammas N3 N gamma sigma V 3 gamma 3 gamma. So, if the total reaction rate is like this for the gamma reactions, then the N gamma is represented according to Planck's radiation law, as I have written in the previous class, 8 pi to the power of 4 13 C cube H cube K T cube, and this makes the ratio of reaction rates 3 gamma sigma V 1 2, okay, ratio of reaction rates forward and reverse if gammas are involved. So, this gives us an expression like this 8 to the power of 8 pi to the power of 5 1 by 2. So, sometimes you need to handle this kind of mathematical expressions, and it is very easy to derive all these things. Please do not leave the derivation part, okay. And here interestingly, not only exponential term, but you also have rest mass energy and also exponential term. If you remember, in the previous case we were getting only exponential term is important, okay. So, this first two terms you can say it is of an order unity, and the ratio is dominated by exponential term, but multiplied by the ratio of rest mass energy to the thermal energy kT, thermal energy kT. Now, because the product reduced mass multiplied with mu c square is greater than or equal to 1 GeV, the factor mu c square divided by kT to the power of 3 by 2 is very large at all temperatures, okay. I am shifting the focus from charged particles which are part of entrance channel and exit channel in general, okay. But when gammas are involved in the exit channel in particular, and when such cases leads to the inverse reaction, that is photo-disintegration, then also we should be in a position to write down the ratio of the reaction rates. Why this expression is important? Because majority of the nuclear reactions are happening as radiative capture reactions in the star. Majority of the reactions happening within the star for synthesis of elements, it is radiative capture. Though they are slow, they play a very important role in the synthesis of new elements. Synthesis of new elements. So, that is the reason it is important for us to write down expression for the ratio of the reaction rates when gamma rays are involved. What did we learn in this expression of reaction rates? In the expression of reaction rates, we have seen that not only exponential term, but mu c square by kT, rest mass energy by thermal energy, this is also there, which is very large at all temperatures, at all temperatures. But we have another term, that is e to the power of minus q by kT. That means at elevated temperatures, photo-disintegration reactions plays a very important role. See, now we are actually discussing the physics part of the, nuclear physics part of the astronomy or features of the astrophysics, right. At elevated temperatures, it is the photo-disintegration reaction, but there also sometimes forward reaction can take place. With what rate these two reactions proceed determines the stellar evolution, and the evolution of a star already have discussed in HR diagram. A star on main sequence can go to white dwarf, can go to red giant, super red giant, it can come back to white dwarf like sun. So, this is some qualitative statement, but quantitatively to get an idea about the which reaction is dominating, it is important to consider the ratio of inverse reaction and forward reaction rates. And when gammas are involved, this expression tells us that at elevated temperatures, photo-disintegration reactions are playing very important role, a very important role. So, I hope it is clear to you how to write down the expressions for reaction rates when gamma rays are involved and when gamma rays are not involved. So, after this, let me touch the topic energy production in stars. Energy production in stars. How to write down the expression for energy production in stars? Can you think? If you know the reaction rate, that means number of reactions taking place per unit time, per unit volume, and Q value of the each reaction. Q value of the each reaction. Maybe we can write down a simple expression for the energy production in stars. Let us see how it looks like. Okay. Let me go to next slide and let me write down energy production in stars. All right. See, one of the important objectives of this course, as I have said earlier, is to understand the energy produced from the stars, isn't it? And energy liberated in nuclear reaction, energy produced in a nuclear reaction is always characterized by Q value. Okay. Now, when we mix with the reaction rate, the total stellar energy, okay, can be given as E12 is equal to Q value, total reaction rate when 1 and 2 are involved, okay, and units are ergs per second per centimeter cube. Now, sometimes this equation commonly is written so that to involve the stellar matter density. Okay. So, in that case E12 is written as QR12 divided by rho in ergs per second per gram. And at high stellar temperatures, as I said, inverse reactions at high temperatures, inverse reactions plays important role, because negative Q value reactions also can proceed because particles are having sufficient energy to induce the reaction. So, in this case E34 can be written as minus Q R34 divided by rho. So, net energy production in a star is nothing but the difference, the net energy production is nothing but E12 minus of minus E34, right. So, here minus is there. So, total it will be E34, but in terms of reaction rate one can write down like this R12 minus R34 Q divided by rho. Okay. So, this is how one can have a simplistic expression for energy produced in stars. Do you remember in the very first lecture and even in the promo video I have told, one of the important objectives of this course to get an idea about the energy production in stars. Who are responsible for the energy production? Nuclear reactions. What kind of nuclear reactions? Forward and inverse at high temperatures. And when star evolves from low temperature to the high temperature region, different types of nuclear reactions taking place, right. Now, if we consider one particular nuclear reaction in forward and inverse, then by knowing the Q value, one can have an idea about the net energy production in the star because of one particular nuclear reaction. Hope you are getting what I am trying to convey. In star, various types of nuclear reactions taking place, and starting from one particular type of nuclear reaction in forward and in reverse direction, taking the reaction rate difference R12 minus R34 and multiplied with the Q and divided with the matter density, one can get an idea about the net energy production in the stars. I hope you have understood the basic concept of energy production in the stars. Now, one interesting feature of this energy production, in nuclear reaction, whatever nuclei are produced, whatever particles are produced, they are absorbed within the star. They are absorbed within the star. However, there is one exception, that is neutrinos. Why it is important when I am discussing this energy production, it will be clear to you soon. Hope you remember when neutrino is emitted. In beta minus decay, beta plus decay, you have seen neutrinos are emitted. and many radioactive nuclei within the star, they undergo decay. So, you can have neutrinos, but these neutrinos, because they travel with velocity of light, and they are weakly interacting with any type of nuclei, very weak interaction, they can just come out of the star as if nothing is there. That is the reason neutrinos can easily be detected on Earth. Of course, you can correlate what I am saying. When I presented various facts as evidence of nucleosynthesis, the detection of neutrinos on Earth, and as I said, billions of neutrinos are passing through our body every time. Where from these neutrinos are coming? The nuclear reactions are happening within the stars, and neutrinos, nobody is there to stop within the star, they are coming out. So, the conclusion is that the energy taken out by the neutrino cannot be included in the energy produced by a star, because that energy is not absorbed within the star, right. Okay. So, neutrinos energy cannot be included to energy of the star, because they cannot be absorbed. If they cannot be absorbed within the star, how can we include in the energy produced by a star, right. Now, you can say, okay, in beta plus decay positron is emitted. Well, this positron immediately will find an electron in the surroundings and it undergoes pair annihilation, and 2 511 keV gamma rays emits in opposite directions. Again, you have the gamma rays, and gamma rays can be easily absorbed within the star when compared to neutrinos. Okay. So, the conclusion to this topic is following: when you are trying to calculate the energy produced from a star, do not include the neutrinos energy, and we will take this very clearly and without failure when I discuss the energy produced in different nuclear processes within the star. Okay. So, there I will consider total energy produced from the star is this, and minus neutrinos energy is the net energy produced by the star. Okay. So, after discussing the inverse reactions and this energy production in the star, let me discuss the last topic in this today's lecture, that is mean lifetime of a nucleus. Nucleus, once it is produced within the star, it will die after a certain time. How? By reacting with another nuclei. Can we come up with some mathematical analysis for this mean lifetime? Let us look forward to it. Okay. So, let me write down mean lifetime of a nuclear reaction. Mean lifetime of a nuclear reaction. So, in the stellar evolution, in terms of time, an important quantity is this mean lifetime. Okay. And the mean lifetime of say nucleus 1 against destruction by nucleus 2. Why I am taking 1 and 2? Because I have been considering this 1 plus 2 in forward and reverse reaction. So, for the sake of convenience, let me represent lifetime of the nucleus 1, nuclei of type 1. When it interacts with the nuclei of type 2, this nuclei 1 is gone, right. That is how you develop the mathematical relation for lifetime of the nuclei of type 1, fine. So, lifetime of nuclei 1 by nuclei y, that is tau, by interacting with the second nucleus, number 1 nucleus is undergoing destruction. So, this can be represented statistically as d n 1 divided by, with respect to time, with what rate it is undergone destruction by interacting with 2, is equal to the decay constant of 1 against 2 and number density of 1, and this is a well known relation you are aware of. The decay constant is always inversely proportional to the lifetime, okay, of nucleus 1 against 2 destruction with 2, okay, destruction against interacting with the type 2. So, this is n 1. So, we can interpret as the change in the abundance of n 1 of nuclei of type 1 as the result of bombardment of particles with particles of type 2. Okay. And decay constant, as I said, it is inversely proportional to the mean lifetime. Alternatively, I can write down this d n 1 by dt when it is interacting with 2 second type 2 minus 1 plus delta 1 2 reaction rate R. So, the change in abundance of N1 is related to the total reaction rate R by this relationship. Why we need to take this delta 1 2? Because for identical particles, two particles are destroyed. And this has value 1 for identical and 0 for non-identical nature. Okay. Now, combining this equation and the equation that we know for the reaction rate, the lifetime is expressed as tau 2, lifetime of 1 against 2 is 1 by N2 sigma V. Okay. So, the mean lifetime of nuclei 1 against destruction by nuclei 2 can be represented like this, and we can also analogously can write down tau of 2 by against destruction by nuclei 1 can be written as 1 by N1 sigma V. Remember that identical particles has cancelled out when we write down the equation. This is the final one. Okay. Now, this tau depends only on N2, you see. Okay. More density of destructing nuclei, second type of nuclei, less lifetime of the first nuclei, first type nuclei. So, N2 and also of course, the reaction rate, and this tau of 1 against destruction by nuclei 2 is quite short if N2 and sigma V are very high. Okay. And for more than one type of destructive nuclei, for example, this nuclei of type 1 can undergo destruction not only by interacting with the particle type 2, but also 3, 4, 5. It can undergo destruction by reacting with any type of nucleus, right. Taking into account the overall lifetime of nuclei 1 can be written like following. Okay. So, it is 1 by tau of 1 is equal to sigma of 1 by tau I by x 1. Okay. So, I value can be I is equal to 1 to n. So, to summarize today's lecture, what I have discussed in the inverse reactions topic, I have expressed the total reaction rate as the difference between forward and inverse reaction rate. Okay. And then I have considered a special case of photo-disintegration reaction, all right, because at elevated temperatures this photo-disintegration reactions plays an important role, and the reaction rate ratio depends not only on the exponential term, but also a very large value at all temperatures, okay, that is ratio of rest mass and the thermal energy, rest mass energy and thermal energy. Then I discussed energy production in stars, and finally I have discussed the lifetime of nucleus by taking example of 1 and 2, where lifetime of 1 is represented against destruction by type 2 nucleus. Okay. In the next lecture, I am going to provide some mathematical expressions for abundance of nuclei. Thank you so much for your attention. Looking forward to meet you in the next lecture. Thank you.